functions connected to stage 2. So now this problem is solved. It's a propyl benzoate. There we go. That's it. So the fun stuff in this one was figuring out the integration, which we had to do by hand. Wasn't given to you. On the exam, most likely I'll give it to you. I go one way or the other. I usually lean towards giving it to you. And usually I even give you a table, so if the data is already tabulated. So that really helps you. Okay? So, all right. But again, I change my mind sometimes. So be comfortable with what we just did here. All right. So we're going to jump into chapter 17. Do the rest of those, and definitely if you want a confirmation on one of them, you can ask me after class or come to my office hours. I'll give you the answers, before the exam. That one's out. It's a little dark in here. Sorry, guys.
That's easy, dude. I'm like. Imines. Benzene with a ketone or a carboxylic acid.
You're guessing. I thought you just told me. No guessing.
Chapter 17.
That's it. We'll be good by next week. Shit.
Chapter 17 is alcohols and phenols. So, of course, prototypic alcohol like ethanol. It's a nice example. There's tons of more examples of alcohols. Some of them are in your book. One of them. Is this one, pseudoephedrine? Which is also pseudofed. In terms of phenols, so phenols are just aromatic alcohols. This is a simple one called methyl salicylate. Also called oil of wintergreen. So I'm going to give you that kind of wintergreen smell. That's that compound. So wintergreen is that compound pretty much exclusively. If you're taking the organic 2 lab, you just used salicylic acid, which is the carboxylic acid of this, to make aspirin. And so that's where you might have seen this structure. That's kind of for the lab people. Okay, so another phenol. Anybody know? This is So THC is a phenol, and it's pretty. I mean, simple molecule, doesn't have chirality like a lot of other drugs. And it's got a hex, 6 carbons, right? 1, 2, 3. That's 5 carbons. A chain on it, yeah. Okay. Cool. And so there's a couple examples. There's tons of examples of alcohols. They're often in a lot of drugs, like pharmaceuticals also. Okay, so let's jump into the nomenclature, and then we'll work our way towards reactivity, all right?
Are we going to have any of those structures memorized?
No. Rather, test you on mechanisms and reactivity and synthesis.
Oh.
Okay, naming alcohols. So I'm not a big nomenclature guy, but there's going to be always a couple problems on the test, and you know they'll be similar to the practice test, so you'll know kind of what they're going to be like. One thing about alcohols is we have a classification system. Classification system where if you have one R group, it's primary, 2 R groups is secondary, 3 R groups is tertiary. So if I say tertiary alcohol, it means you got 3 R groups, etc. Okay? All right, so IUPAC. Marker's slowly going out, but I'll change it in a second. IUPAC, you basically pick the longest chain and add OL. Okay, and so like hexanol or pentanol, etc. Begin numbering near the OH. Number your substituents. Right name. Okay, so that's this general strategy. It's kind of similar with what you've seen before, like alkenes and stuff like that. So this kind of alcohol, find the longest chain, 2, 3, 4, 5, 6. It's a hexanol. Did I do it right? 1, 2, 3, 4, 5, 6. Got hexanol. And we're going to say it's, where's the alcohol is on carbon number 3. We're going to say it's 3 hexanol. And we put, I usually write the name kind of from the end forward. Okay? So 3 hexanol, and then we have a wet on position 4. 1, 2, 4, 4 methyl. And put a dash there. 4 methyl 3 hexanol. That's pretty good. All right. So the first thing to recognize in this problem is what this kind of benzene is called in terms of, like we're considering it a substituent on the chain. And what's that substituent called? Phenyl. It's going to be a phenyl substituent. So phenyl substituent. So we'll give it a number. It'll be called something phenyl, right? Okay, so this is pretty easy. 1, 2, 3, 4. It's a butanol. Butanol 2. So 2 butanol. And what else? We got a phenyl and a methyl, right? And who wins alphabetically? Methyl. So when you do the substituents, you list them in alphabetical order, right? So you list the substituents in alphabetical order. So we have a methyl and a phenyl. Methyl will come first. I'm gonna, that's 2-methyl. 2-methyl, 1, 2, 3, 4. Phenyl, 2-butanol. And then, yeah,
Are there exceptions to the alphabetical rule?
pretty sure there's not.
Okay.
Pretty sure there's not. I think it's kind of a general thing. It's just that it resolves kind of how to name things. There might be, but yeah, I'm pretty sure, at least for a class like this, we just kind of go with the alphatizations or when we list our substituents. Yeah. 2-methyl 4-phenyl. Cool. All right, there's our IUPAC name for that molecule. All right. What else? A couple more. Okay, that's a cyclohexane with a diol on it. Cyclohexane. Now diols, we say diol, D-I-O-L, 2 alcohols. Cyclohexane diol. Are you sure it says? One's going up, one's going down. Trans. And it's going to be 1, 2, cyclohexane diol. And it's trans. Trans, 1, 2, cyclohexane diol. Yeah. Cool.
One question.
Yeah.
So if you were to draw the same molecule, like in a not in a chair form, but in like the regular
Yeah.
form, so the name would change.
Now, what,
No.
Okay. Yeah.
yeah. The only thing we're not addressing here is the absolute stereochemistry of the centers. So I could actually assign RNS to this. I'm not going to do that. Okay. For most intents in this course, I'm not going to worry about RNS just because I don't want to get back into that can of worms. It's not that bad. I don't know how long you guys will learn that. I don't want to go back to that. Okay, what's this molecule called? Not benzene.
Phenyl.
Phenol.
Ah.
Not phenyl.
It's my accent.
Phenol. It's different. Phenyl is a. This is phenyl. This is phenol.
That's what I said.
Phenol is a molecule that looks like that. And if we were yeah, this maybe parabromophenol would be or 4-bromophenol. 4-bromo or para bromo. Those are acceptable names. Okay? 4-bromo, parabromo. All right, cool. All right. Onward. Those markers buggy me. No, it's not good either. Okay, properties of alcohols. In general, higher boiling point than hydrocarbons. Which kind of makes sense. So if I have propanol and ethyl chloride butane, let's think about the molecular weights of these and the boiling points. Molecular weights are almost identical. 60, 65, 53, so roughly, ballpark. The boiling points of these are 97, 13, these are degrees Celsius, and -1. So -1. So obviously something's going on, and the boiling point of alcohols is a lot higher, even though it's roughly the same molecular weight. And what's the reason?
Hydrogen bonds.
Hydrogen bonds, yeah, nothing magic there. You know this stuff already. So we have an extensive network of hydrogen bonding, and that's one of these intermolecular forces that keeps things like in the liquid state, for example. And so, just like water, same principle, right? You guys know that? All right, so intramolecular would be within the same molecule. Intermolecular means it's a network of different molecules. Yeah.
I was gonna say, wouldn't polarity also, like with the Cl, wouldn't you take that into
Yeah,
account?
yeah, that's a good point. Yeah, why is chloro ethane a higher boiling point than butane? What's that?
Electronegative.
But it's like it's a dipole forces. Yeah, so it's delta negative, delta plus, and the dipole forces are almost like hydrogen bonding, and there's like a stacking effect, and then the dipoles kind of interact on the molecule dipoles. So it's another interactive force. Yeah. Okay, branching effects. This one's interesting. Boiling point, 118, 182. So they're all isomers they're all 4-carbon alcohols. N-butanol, sec-butanol, and terbutanol.
Just like with the structure, geometry.
Why does the easiest way to think about it initially is why N-butanol, the first one, has the highest boiling point.
So the geometry of the.
Not really geometry. It says there's London dispersion effects where atoms bounce into other atoms and make these temporary dipoles, right? And which one has the most surface area? The long kind of snake-like one. So the long snake-like one has more surface interactions. With more surface interactions, you get more intermolecular forces. So surface area effects. And that affects London dispersion.
It was intra, right?
In the hydrogen bonding? Or,
No, this.
This is the inter.
Inter.
Yeah. Intra would mean within the same molecule. But this is actually like one of these reacts with another one, right? Or interacts with another one. So and there's like a lot of these interactions where they bounce into each other and create temporary dipoles, and that's an interactive or it's an attractive force. So you have that in the long snake-like one, but in the one where everything's kind of squished together, you don't have that. It's a very small little ball, and you don't have as much surface area interactions. So in general, the kind of long linear chains have more interactions. Okay? All right, good. Acidity, basicity. So alcohols can be basic and they can be acidic. They have lone pairs, and they also have protons. And so the lone pair can act as a base, or it can donate its proton and be an acid. So it's kind of like a dual role there. If you have a strong acid, can totally protonate in alcohol. And it's called oxonium ion. And that